Welcome to this explainer. Okay, think about the very last time you did a load of laundry. You probably just threw in some clothes, poured a little liquid or powder into a cup, hit a button, and walked away. I mean, it really feels like the most mundane chore in the world, doesn't it? But what's actually happening inside that machine is literally a microscopic miracle. We're talking about a highly engineered, finely tuned chemical symphony working to lift grease, suspend dirt, and soften water, all while keeping your favorite shirt completely intact. Okay, let's dive into this. Here's our roadmap for today. We'll be taking a journey from microscopic chemical thermodynamics all the way to macroscopic industrial chemical engineering. First, we'll compare soap and synthetic detergents. Then we'll unpack the actual chemistry of cleaning, followed by the crucial role of builders. After that, we'll look at liquid versus powder formulations, and finally, we'll wrap up with the massive scale of the manufacturing process.
Section 1. Soap versus synthetic detergents.
All right, I want to shatter a common misconception right out of the gate. Detergent is not just soap. We tend to use those words interchangeably, right? But chemically speaking, they are vastly different beasts. Soap has actually been around for millennia. It's a salt of natural fatty acids. But it has a pretty fatal flaw, and that is hard water. You see, the polar carboxylate in natural soap loves to bind to the calcium and magnesium ions found in hard water. And when it does, it creates this insoluble, scummy precipitate instead of actually cleaning your clothes. Detergents, on the other hand, were engineered specifically to defeat this exact antagonist. They're synthetic compounds like alkylbenzene sulfonates. Because their polar sulfonate group is way less likely to bind to those pesky calcium ions, detergents remain highly soluble and active, even in the absolute hardest water. Now, before we go deeper into the chemistry, we've got to acknowledge the sheer power of these everyday chemical cocktails. Because they're so highly engineered and incredibly effective, they absolutely must be handled with respect. Careless use of detergents is actually a primary cause of childhood injuries from cleaning products. To put that into perspective, in the US alone, a child is rushed to the ER every 35 minutes due to these exposures. And the risks just multiply when we store them in low accessible spots, transfer them to unmarked containers, or, and this is a big one, leave highly concentrated laundry pods unattended. It's a sobering reminder that we're dealing with very potent chemicals every single laundry day.
Moving on to Section 2. The chemistry of cleaning.
Okay, so it's time to introduce the absolute hero of our story, the surfactant. Now, what's really interesting about this slide is the dual nature of this anionic surfactant molecule. You can see it's basically split into two distinct parts. Part A is this long hydrocarbon tail. This tail is hydrophobic, meaning it literally fears water, but it absolutely loves oil and grease. Then you have Part B, the head, which is the sulfonate group carrying a negative charge. This head is hydrophilic, so it loves water. This split personality, that is the fundamental secret to how detergents actually clean. So, what actually happens when you throw a bunch of these split personality molecules into a washing machine? Well, they group together to protect their water-fearing tails, forming this cool spherical structure called a micelle. The water-loving heads face outward toward the water, while the oil-loving tails hide inside, facing inward. When they bump into dirt or grease on your clothes, those tails dive right into the oil. They effectively surround it, trap it right in the center of the micelle, and suspend it in the water so it can just be washed away. It's like a microscopic search and rescue mission for dirt. But wait, how exactly does the soil get off the fabric in the first place? Well, it all comes down to thermodynamics, specifically something known as the Lanza process. For soil to clean spontaneously, the free energy in the clean state has to be lower than in the dirty state. Here's how it breaks down. Step 1. The surfactant absorbs onto both the fabric fiber and the fatty soil. Step 2. This action dramatically lowers the interfacial tension relative to the water. And step 3. Because that tension is lowered to a critical point, the soil just spontaneously removes itself from the fiber. So yeah, the actual physics of dirt removal broken down into 3 elegant steps. Let's actually see those thermodynamic steps in action through what's called the rolling up mechanism. Look at condition 2, and then see how it moves to conditions 3 and 4. As the detergent solution alters those interfacial tensions we were just talking about, the droplet of oil is quite literally forced to roll up into a little sphere. The contact angle between the oil and the fiber just keeps decreasing until pop! The oil droplet detaches completely, floating off into the wash water. The surfactant basically chemically rolls up the oil and lifts it right off your cotton shirt. How cool is that? All right, Section 3, the role of builders. Now, our hero surfactants are pretty incredible, but they really can't work alone. This is where builders, also known as sequestrants, come in. These are chemical ingredients designed specifically to mop up hard water ions, namely calcium and magnesium. Think of builders as the heavy-duty bodyguards for the surfactants. If the builders weren't there, the hard water ions would literally attack the surfactants, completely deactivating them and turning them into useless scum. So the builders basically take the hit so the surfactants can do their job of actually cleaning your clothes.
So, builders basically have two completely different battle tactics against hard water: complexation and precipitation. In complexation, the builder reacts with the metal ions to form a water-soluble complex. This keeps the calcium trapped, but still dissolved in the water, so it can safely be washed away. In precipitation, on the other hand, anions from ingredients like carbonates form completely insoluble salts with the calcium. This creates a solid precipitate that physically drops out of the solution. And what's wild is that in any given wash, there's a constant competitive reaction between these complexing and precipitating anions, basically fighting over the calcium. And this brilliantly illustrates complexation in action. What we are looking at here is the chemical structure of a seriously powerful builder called sodium tripolyphosphate, or STPP for short. Notice how the oxygen atoms in the STPP molecule are structurally wrapping around and trapping that calcium ion right in the middle. Once the calcium is locked inside this sort of molecular cage, it is completely neutralized. It has zero chance of interfering with our surfactants.
Next up, Section 4, Liquid versus Powder Formulations.
Okay, so we've got our surfactants and builders, but a modern detergent is honestly a marvel of consumer formulation. Let's look at the sheer variety of ingredients required to make this work. We have our surfactants doing the active soil removal, right? But then we also need hydrotropes, especially in liquid detergents, to ensure all these chemicals stay happily mixed together and don't separate while sitting on the supermarket shelf. Then we add enzymes to specifically attack biological stains, things like proteins or starches. And we even include fluorescent whitening agents. These are wild. They actually absorb invisible UV light and re-emit it as visible blue light, making your white clothes look brilliantly, almost impossibly clean. But putting all of these together, that is a massive, high-stakes balancing act. Formulators face some serious challenges here. First, they have to balance surfactant levels, which often make up 30 to 35% of the mix, against target costs and local water hardness. Then, they spend months adjusting those hydrotropes, like propylene glycol, in intense storage trials so your liquid detergent doesn't turn into a separated, chunky mess. Plus, enzymes are incredibly sensitive, so they have to be carefully stabilized with things like boric salts. And through this entire process, they must strictly control the pH. If the pH goes too high, it completely destroys the enzymes. But if it drops too low, the cleaning power absolutely plummets. It's a real tightrope walk.
Finally, let's move to Section 5, the manufacturing process.
Let's move to and see how this builds at an industrial scale. Once the chemists finally nail down that perfect formula, we have to actually make the stuff. It's genuinely awe-inspiring to think about the juxtaposition here. We started this explainer looking at microscopic micelles measured in mere nanometers, and now we're looking at a towering, massive industrial chemical engineering plant. These spray drying towers are gigantic, highly capital-intensive structures. Just one single modern unit can churn out over 80 tons of detergent powder every single hour. That's literally the weight of dozens of cars every single hour. The journey of a powder detergent through one of these massive towers is intense. It's rapid, and it happens in 5 distinct steps. First up, slurry making. All those robust ingredients are mixed with water in a giant vat called a crutcher. Second, pumping. This thick slurry is forced at extremely high pressures. We're talking up to 100 bar through a series of filters. Third, atomization. The slurry gets forced through tiny nozzles, creating this fine mist of droplets right inside the tower. Fourth is drying. These tiny droplets fall through a 10-meter wide cylinder while a massive blast of 300 degrees Celsius hot air rushes upward, instantly flashing the water into steam. And finally, cooling and classification. The newly dried granules are collected, cooled down, and carefully sifted to get the absolute perfect size. And this right here is the result of that violent drying process. As those wet droplets fall and dry in that crazy, turbulent 300-degree air, they don't just form perfect little spheres. Instead, they violently crash into each other and agglomerate, resulting in a final product that looks a lot more like irregular, knobbly bunches of grapes. But here's the thing. This irregularity is actually by design. It is perfect because it helps the powder dissolve super quickly the moment it hits the water in your washing machine.
Now, let's zoom way back in to tie our macro manufacturing story back to the micro level. What you're seeing is a scanning electron microscope image of just one single spray-dried particle. Look at that complex internal porous structure. The rapid expansion of steam during that intense drying phase literally puffs up the droplet, creating all those little tiny cavities. This gives the powder a lower bulk density, which, believe it or not, is exactly what consumers prefer. And it ensures that water can quickly penetrate and dissolve the granule to unleash all those surfactants and builders waiting inside.
So, the crucial takeaway here is this. Laundry day is anything but ordinary. It is the final culmination of organic chemistry, thermodynamics, complexation reactions, and massive industrial engineering, all neatly packaged in a cardboard box or a plastic jug. Next time you run the wash, ask yourself, are you just doing laundry, or are you actually conducting a high-stakes chemical symphony? Thanks so much for joining me on this explainer, and keep asking questions about the hidden science of your everyday life.